for this one. So essentially what the squeeze or the sandwich theorem says is that if f is always between h and g, and you can see that illustrated in the graph right here, you see how f, vertically speaking, is always between f and g, or sorry, between g and h. If that's true, and the blue graph and the pink graph kind of squeeze down, if that f is going to still be between them, doesn't the f have to squeeze down in the same spot? Seem logical? Like if they're getting squeezed down, I'll use a football analogy again. If somebody's running up the sideline and a defender runs at an angle towards them and they all meet at the sideline, right? Kind of the person with the ball is between the sideline and the defender. They're eventually going to sort of coincide, right? They're all going to be like right in the same spot. And that's what's going on here. The G and the H are kind of headed on a collision course, and the F is kind of caught in the crossfire, right? Caught in between, it's going to be in the same spot. Make sense? So here's the formal statement of it here. If F is between G and H, vertically speaking, and H and G's behavior is headed toward the same place, then F's behavior is also headed to that same spot. Notice in all those cases the limit was equal to L, and so they're all heading towards this Y value of L. This holds true because f of x is always between on the interval that we are discussing. So I think 8 is a pretty nice example of this. We can look at a graph of this here in a second as well, I suppose. It says if 4 minus x squared is less than or equal to f of x, which is less than or equal to 4 plus x squared, then find the limit as x approaches 0 of f of x. Well, all the limits that we've been doing, if you just look at what I've got there in the blue box, there's like not enough information, right? You see how somebody could look at that and be like, well, what is f of x? I think I can do this limit as x goes to 0 thing, but I don't even know what f of x is, so I can't do this. The good news is we do have this other information, the fact that f of x is between those other two graphs. So, with that in mind, can anybody tell me what 4 minus x squared looks like on a graph? Any takers? Y equals 4 minus x squared, chance?
Isn't it just like an upside down parabola?
Upside down parabola moved
Up 4.
up 4. You got it. All right, so I'm going to graph that. So here is my upside down parabola. Shifted up 4. Okay, so that's one of the boundaries for f. And then 4 plus x squared is the other boundary. And what does that graph look like?
It starts at where the vertex of that one is and goes up.
It's parabola, right?
Yeah, parabola.
Awesome. Okay. That was not a very good start. There we go. And it does kind of meet right there vertically at y equals 4. Now, we have no idea what f looks like, so I'm just going to make something up. The only thing I do know is that it's between those two graphs. I'm just going to say it looks something like that, and I frankly have no idea what it does. The main thing I do know is that it's between those two graphs. So, then as we look at this question, the limit as x goes towards 0 of f of x. Could look at that, and based on the graph there, based on understanding what those two parabolas are doing, I can say, well, as x gets closer and closer to 0, my green graph, which is f, gets pinched down right between them, right? Therefore, this limit has to be what? It's got to be 4. And your reasoning there could involve a graph, I suppose, but you could say, I use the sandwich theorem based on the inequality that was given to us up here. I know that for sure that f is going to get pinched down between those two functions. So, a bad question, like if I were to give you the exact same setup and then ask you to find the limit as x goes towards 5 of f of x, why would that be sort of a bad question to ask? Yeah, nothing's getting pinched down right there, right? We know that the green graph is somewhere in between. We could probably come up with a range for what the limit would be, but we certainly couldn't say it's exactly this number. So the pinching theorem here would really only apply to what's going on around 0 as opposed to some other number. Okay. You guys have any questions at all? Okay, fantastic. Let's go back to the place I was heading towards before. which is over here. So I think, as I mentioned earlier, I think that you guys certainly are capable of doing some thinking here with 1 and 2 as far as determining what kind of discontinuity, if any, there are with these two. So take a couple minutes and at least see what you can do with either one of them. If you can get them both done here in a few minutes, that's great. And then we'll check your answer. I'll be around to kind of help and support as needed. Okay, I want to run through these quickly and then we'll go back and kind of loop back through and go a little deeper. So with number 1, what kind of a discontinuity did you guys see with number 1? It is removable. I totally agree. What about number 2? Number 2 is definitely a jump. Let's talk about how you could kind of show this. I'm thinking that here with number 1, perhaps the easiest approach to this would be to say you could factor the top. And the top factors is the difference of 2 squares. And you do something like this, right? Oh, it's frozen, sorry. I always forget. There we go. And anytime you cancel out a factor in the top and the bottom, isn't that the very thing that creates a removable discontinuity? That creates the whole. And so I think at this point we could look at what results. Of course, what results is just x plus 1. That's not going to have any discontinuities, but the fact that we canceled out a couple of factors like that means that g of x has a removable discontinuity at x equals 1. Sam, your question.
Yes, could you explain more about a removable discontinuity? I know in the video it said something about like describing it as a piecewise function.
Sure.
Along those lines.
So what we could do, the reason why we call it removable is because you can literally remove the discontinuity. So like this graph for g of x looks like, so it's x plus 1, but it's got that hole right there at 1. Make sense? So this is g of x right here. So if I wanted to, what I could do is I could say, you know what? I would like this graph to be not continuous. Or excuse me, I would like this graph to be continuous. I'd like to get rid of that discontinuity. So what I could do is I could say, you know what? I am going to redefine another function just like this one, but I'll do it piecewise and I'll fill up that hole. So what I could do, I could create the same graph, but I could do it like this. I could say h of x equals g of x as long as x doesn't equal 1. Make sense? Because that's where that hole is. And then I'd say h of x also equals 2 if x equals 1. So if I did it like that, I have the point 1 comma 2, which would then go back and fill this hole, creating a continuous graph. So in other words, if you have just a hole, you could take that graph and fill the hole and create a continuous graph. That's why it's called removable discontinuity, because you can literally just get rid of it just by defining another piece to add to that graph. Same is not true of vertical asymptotes or jumps. It is true of a hole like this, though.
Great, thank you.
Make sense? Okay, cool. Any other questions? Okay, so you guys said that number 2 had a jump, and I totally agree with you. I think probably the best way to illustrate a jump like this is to use that continuity statement that I showed you in the video, and we will use this a lot here today. If I were to say, and by the way, let me go back. I think this is worth talking about as well. If you look at the left piece, which is that one right there, what would 4x minus 1 look like on a graph? Y equals 4x minus 1? Sorry?
Line.
It's a line. Yeah, just regular old line. Yep, you guys have the right hand motion there. And aren't lines always continuous and differentiable? Like there's no issues with continuity for sure, and we'll talk about differentiability later. What about this piece down here, the right piece? X squared plus 1 will look like what? Parabola, and aren't parabolas also always continuous everywhere? So there is no issue whatsoever with continuity on this whole graph, except maybe at 0, right? Because that's where these two pieces at that point are supposed to join. And so we got to check that part out. So I'm going to say the limit as x goes towards 0 from the left of h of x possibly equals the limit as x goes towards 0 from the right of h of x, and that is supposed to equal h of 0. So then as I analyze this, I say, all right, well, from the left of 0, that would be the line. So that limit would be -1 just by direct substitution. 4 times 0 minus 1. Does that make sense? And then The right piece would be 0 squared plus 1, which is 1, and obviously those two are not equal. So the left-hand behavior and the right-hand behavior are different, and that is exactly what creates this jump. So let's see here. That's the left piece, so it's going to do something like this. That's what that graph would look like. You've got a line on the left, you've got a parabola on the right, and I don't know if the parabola is oriented correctly as far as is it opening, or is it where the curvature actually is, but it looks something like that. And therefore, you've got this jump discontinuity because of the different behavior from left and right. Does it make sense? Okay. Do you have any questions? Okay. I think we have some pretty challenging questions coming up here, so if you guys would, look on ahead to number 3. And I think this is another good discussion. Yes. This is really similar to sort of like a backwards way of looking at the question on the video. So it says, if f of x is not continuous at x equals 2, which of the following must be true? Gives you 3 options. So you do have a 33 and a third percent chance of guessing. But I'd like for you to do a little more confidence beyond just guessing. So talk it over. I would suggest you think about graphs here. See how it goes. Ready? Just a little bit of help. Let's think about it like this. Just focus on A for a second. What kind of discontinuity is A illustrating? A jump, right? Why do you say jump?
Because it's like approaching from this hand motion again. Approaching like to here from this side, approaching to here from this side.
Different behavior from left and right. You're exactly right. Okay, so this is definitely a jump discontinuity. B. What is that? What kind of discontinuity or discontinuities is that describing? Say again? Okay, so the whole, or the removal, I'll just put RD for removable discontinuity. Is it possible that there's another type of discontinuity that would fit with that? An asymptote, right? Not defined, right? It could be a vertical asymptote. Okay. And then C. What kind of discontinuities could that be talking about? Sir, Luke.
Like a hole with like another point somewhere else on that x value.
Okay, so I'll put RD with point. Agreed. I think this is what he is going for. I agree. I think that certainly works. Any of the other ones fit with that one? Okay, so armed with that information, if you want to change your answer, feel free. Maybe you think you've got it. I'd like to do a vote again, kind of like we did the other day. So how many of you are convinced for sure you think A must be true? A has to be true. Anybody agree? A has to be true? Okay, so the fact that you are, unless Chance just said maybe A?
Yeah,
No?
sure.
Maybe? Okay. So A is definitely, sorry Chance, not it. You just kind of threw your hand up there at the last second.
Yeah.
And here's why. Think about what this is saying. It says, if f of x is not continuous at x equals 2, which of the following must be true? So if you select A, you're basically saying it has to be a jump. Right? Has to be a jump. And that's not true. It doesn't have to be a jump. It certainly could be. So again, if you place the word must with could, then I think all these would be correct, wouldn't they? Could would, ABC would all be correct. But it says must, and I don't think that it has to be a jump. So I'd say A is out. B, does it have to be a removable discontinuity or a vertical asymptote? Does it have to be one of those two? It really doesn't, does it? So if f of x is not continuous, couldn't it be any one of 3 potential discontinuities? So, I mean, B, unfortunately, that's not it. So really, by process of elimination, you get down to C. But Luke correctly said, hey, you know what? C could be illustrating a removable with a point, right? But I think there's a little bit more to that, right? Couldn't C be illustrating a removable with no point? Because couldn't f of 2 simply not exist? Therefore not equal to whatever the limit is? Okay, so let's keep thinking here. So could it be a vertical asymptote? I think so, because if it's a vertical asymptote like this, then f of 2 doesn't even exist, and neither does the limit, right? And so you can't say, hey, dne equals dne. I mean, if they're both dne, the limit simply does not exist, right? So it could be a vertical asymptote, and it also could be a jump based on the description in C, because f of 2 could be right there, and the limit could be dne, right? Or really it could be different behavior from left and right with f of 2 right in the middle, or somewhere else vertically speaking right there. And so C is the most general statement. It's basically an adaptation of this, limit as x approaches 2 from the left equals limit as x approaches 2 from the right equals f of 2. Right? They basically have just taken this and condensed it down into one statement. So C. I saw some folks that circled C there, so that is the correct answer here. You're starting to get a glimpse of the 2 inches wide but 2 miles deep. You got to really dig deep. It's gonna involve some reasoning, and I think that is one of the greatest gifts that you could get as you work through and eventually leave and hopefully successfully leave a class like this. I hope you do some math and calculus, in your future. But if the one thing that gets strengthened is your reasoning and your logical ability to work through a problem, if that gets strengthened, I think it's a win, a big win, right? And if you do some calculus and you get a 5 and all, that's certainly awesome too. But if you can strengthen your reasoning, it's fantastic. If you're more logical, that's great. Make sense? Question, Gretchen.
Yeah, I'm just wondering, so the one that you drew that has it goes in different directions, to infinity, that is an illustration of C, or it's not?
It is. C could be that. Yeah, so I can go a little bit deeper with that. So C says f of 2 does not equal the limit as x approaches 2, right? So if you have this, whatever, something like this, then wouldn't you say, based on that picture, that the limit as x approaches 2 of f of x doesn't exist? In fact, I should probably just write it like this. Okay, so whatever f of 2 is, whether f of 2 exists or not, because f of 2 could exist. It could be like right there. You could have a piecewise doing something like that. So even if f of 2 does exist, you'd say, well, does f of 2 equal dne? Nope. And if you took away that, now f of 2 doesn't even exist, so you'd have a dne doesn't equal dne, right? And so you can't say, hey, these two dne's are the same, therefore I don't know what, right? And so, so the dne side is like thinking about, well, okay, if one or both of those don't exist, what does that mean? That's kind of the thing that's not apparent right on the surface. Thanks for asking. Anybody else with a question like that? Okay. All right, cool. All right, so our next task is right here, number 4, and I would say, yeah, for sure. So number 4, I would say that I hope you guys can take this hint. The odds of you taking a quiz or test from me, or maybe the College Board AP sort of test, and not seeing a question like this, slim, real slim. Okay, real slim that you wouldn't see this. And as a matter of fact, I have to be honest with you. I do respect your effort and your time. Like I said before, I am a student, and so I know what it's like to feel like your time has just been totally wasted, and I don't like that, and I'm sure you don't either. All of the examples I have in here for you guys, they're put in here with a purpose. Like these, you have the advantage of these notes having been refined over the course of 20 years. And so I hope that it's like 99.9% time waster free. I know for sure it's like maybe like a 0.01% better than last year, maybe something like that. I don't know. Just know that as you look through these examples, please don't think this. Maybe you've experienced this in math classes before. Please don't look at number 4 and be like, whoa, number 4 was kind of challenging. There's no way he put that on the quiz. Would, for sure. Make sense? So please don't look at some of these as just sort of like gimme throwaways, like, yeah, he'd never ask me about that. I will. I promise. I don't want to waste your time, because I feel like that's sort of a waste of time if I'm just going to be like, yeah, I'd never ask about that. Well, why are we doing it? Right? All right, so here we go. If g of x equals that piecewise function, find the value of a so that g of x is continuous for all x. So let's think about this for a second. This bottom piece is a line, and the top piece is a what? Cubic, yeah, you kind of had the hand going there, yeah. So it's a cubic and a line. The line is set, right? The line is negative 3/4 x minus 2. There's nothing we can do about that. But the cubic has this ax cubed plus 4. What effect would the a have on the cubic? Whether a was like positive, negative, or fraction, or not a fraction. What's one thing?
Kind of like the slope and how steep it is and how quickly it will get to that.
Right, it's going to steepen it or flatten it? Totally. What else could it do?
Invert.
Yeah, exactly. You could flip it upside down. Like whether a was positive or negative, it would either go like this or like this, right? And so what we need to do here is we need to figure out what a is so that we can arrange a perfect meeting of the two pieces of the function, right? So basically what I've got is I've got this. Don't scratch this graph out. This is just be an illustration. So here's negative 2, and negative 3/4 x minus 2 is going to be like, I don't know, something like this. And then I've got this cubic, and I know I've got this plus 4, but the cubic could do, I don't know, it could do like something like this. It could do something like this. It could be stretched in such a way that this drops down to here, and it actually does this. It could be stretched too far, it could do this. Or I could get it exactly stretched, and maybe it has to open down or something like that, right? So I'm trying to get the a value exactly right because there's only one spot where it can be in order for this to be continuous. Any other spot, we're going to have a jump. That make sense? I'm trying to get that a exactly right so it'll stretch out or shrink down or whatever it needs to be and open up or down correctly so that it'll perfectly meet with that line. Okay, so here's what we do. Anytime you are asked to make a function continuous or anytime you're asked to prove that a function is continuous, I want you to start with those one-sided limits. One-sided limits. This is that little statement that I showed you in the video. So here it is. I'm going to say the limit as x approaches negative 2 from the left of g of x has to equal the limit as x approaches negative 2 from the right of g of x, and that has to equal g of negative 2. So that statement has to be true in order for g to be continuous. Make sense? Left-hand behavior, right-hand behavior have to be the same, and the value of the function has to be the same as the behavior. Okay, so the left piece is the line. So I'll put in a little extra step here. I'll say limit as x approaches negative 2 from the left of negative 3/4 x minus 2 then has to equal the limit as x approaches negative 2 from the right. This is the cubic, ax cubed plus 4. And which of the two pieces actually contains g of negative 2? The cubic or the line?
Cubic.
The cubic has it, yep. So this would be a times negative 2 cubed plus 4. We're going to find that that last piece is going to be redundant here in a second, so that'll drop off. Still making sense? Just kind of adapted it to my specific pieces here. Okay, anytime you've got a limit and you're trying to evaluate it, what might be the best and first thing you should think about as far as a method? Yeah, plug it in. Just try direct substitution, totally. So if I do that, see here, negative 2 going in there for x on the line, it would be negative 3/4 times negative 2. So that would be negative 3/2 minus 2. And that would have to equal a times negative 2 cubed plus 4. You guys notice how that's the exact same thing as the third piece? So I could write that again if I want to, but it's redundant. So I don't really feel compelled to write it a second time. So at this point, what we have here is a nice, pretty handy linear equation to solve for a. Negative 3/2 minus 2 should be negative 7/2. This is negative 8a plus 4. And now it's just a matter of subtracting 4 and dividing by negative 8. So if I subtract 4, let's see, it'd be negative 8/2, so negative 15/2 equals negative 8a. If I divide by negative 8, I'm coming up with 15/16. is A. Did I do my arithmetic right? Yeah, you guys agree? Okay.
So it's negative 3 times, negative 3 halves times negative.
It's negative 3 halves minus 2. So what I did there is I did negative 3 halves minus 4 halves. I got my common denominator, so I said negative 7 halves. Then I subtracted the 4 over, so I said the 4 was 8 halves. So negative 7 halves minus 8 halves would be negative 15 halves.
But if you plugged in a negative 2,
That'd be a positive.
Like-
Negative 3.
Oh, darn it. Yeah, you're right. I literally I asked, did I make a mistake? I was like, I'd say 98% of the time I don't make mistakes, but every now and then I do. So that was a total honest mistake. Let's go back and fix it. Positive 3 halves. And I'm recording this on video, and I'm not going to go back and edit it. I'm not ashamed to say that every now and then I make a mistake. It's okay. So let's see here. 3 halves minus 2 would be negative 1 half equals negative 8a plus 4. So this ends up being negative 9 halves equals negative 8a. So I got 9/16. Is that better? Okay. Sorry. Yes, your math teacher every now and then messes up. It's okay. Kayvon, go ahead.
Can you go over what you got the 3 seconds again, please?
Oh, yeah. So what I did, like the little step in between here, is what I said right before that is I said something like, if you're ever trying to evaluate a limit, consider just plugging in the number. So I have negative 3/4 times negative 2 minus 2. And so I said negative 3/4 times negative 2 technically is 6/4 minus 2, and 6/4 reduces down to 3 halves. That make sense? Okay. Yep. Anybody else with a question, concern? Okay, so basically what we found here is that if A is 9/16, this cubic is oriented correctly and stretched out or squished down just enough to where it will exactly meet the line when x is negative 2. Kind of like that graph I drew earlier. Okay, we good? Okay, let's at least do one more here. Let's take out number 5. This will get us pretty close to the IVT. I know we're done at 55. We'll just see how this goes. So here's number 5. Okay, so this says if h of x equals that piecewise function, what do these two words mean right here? Show that. Prove it. Yeah. In other words, show some steps. In other words, it's basically telling you we think h of x is continuous. So we're already kind of telling you the end of the story. We just want to see the pages in between. We want to see like how is it actually true? Can you prove it? So I would suggest this. I'm going to let you guys take this on for a few minutes here. I would suggest that anytime you're asked to prove that something is continuous or prove that it's not continuous or whatever, strongly consider one-sided limits equal each other equals h of 4. Make sense? That limit, one-sided limit statement that I just used and used in the video, I would consider using that as a start. So give you guys a couple of moments here to try this out. Later, and just for your own enjoyment, I'm seeing a lot of good work here. I hope that everybody has this and certainly discuss as needed. I saw a ton of folks that started off with this. They said limit as x approaches 4 from the left of h of x equals limit as x approaches 4 from the right of h of x is equal to h of 4. That is a really fantastic start. I was talking with Tim over there, and if you get some math teacher in the future that is like super stringent about rigorous proofs, technically, I've written it a few times, these equal signs should have little question marks over them because we haven't established for sure that those things are all equal yet. In a minute we will, but at this point in the game we're like, well, we think they're equal, but we don't know for sure. So the question mark should be there. I will not mark you off for that. Neither would an AP reader. So don't stress about it. Just know that if somebody's super rigorous, they might want you to do that. Okay, so then direct substitution. So let's see here. The left piece is the line there. So this would be 1/2 times 4 minus 48. I think maybe I could drop them at this point. I'll leave it in there for now. The other piece would be the parabola. Plus 2. And of course, h of 4 is contained within the line, so I don't need to write that again. Okay, so then this ends up being 2 minus 48, so that's negative 46. And that definitely does equal negative 48 plus 2, which is also negative 46. And those are all equal to h of 4. It's supposed to be a 4. There we go. And so we've done it, right? We've proven that the left-hand behavior and the right-hand behavior and the value of the function are all the same thing. So we can say, therefore, h of x is continuous for all x. What do you think? Any questions? So, yeah, go ahead, Sam.
Do those dots mean therefore?
They do. Yep, that's standard math notation for therefore. So feel free to do that instead of writing the word therefore. And we'll use that a lot. Definitely. Okay, so I want to do at least one more activity here, and I'm looking forward to seeing what you guys do with number 6. This will really, hopefully, tie some good things together here for you. So please do look at number 6. It says, if g of 3 equals -5, what is the limit as x approaches 3 of g of x? Ready, go. X isn't kind of the real tempting thing to do. It's just to be like, oh, well, of course, this must equal -5. Like for someone that is like maybe knows just enough to be dangerous, they might just like jump to that conclusion, right? But of course, that we can't support that, can we? Can't support that at all. That's not necessarily going to be it. If I know that g of 3 equals -5, all I really know is that when x is 3, y is -5. I basically know that. And I'm asked about the behavior of g on either side of 3. Well, isn't it certainly possible that it could look like this? That's very possible, but it is not for sure. I heard a lot of people say, well, hey, couldn't it be this? And so wouldn't the behavior here be totally different from the actual g of 3 equals -5? Be totally different behavior. So that's not it at all. Gosh, I mean, couldn't it be like this? Could be that as well. It could even be this. Something like that. I mean, I'm sure there's other opportunities to draw some other graph as well. So, Jake was like, well, isn't this sort of one of those not enough information sort of scenarios? And I'm like, kind of. There's one really specific piece of information that I didn't give you that would have made a difference. Say again? Okay, yeah, the equation for sure, but let's take like a little more of a general approach. Like, what about g of x, beyond going all the way to knowing the actual rule for it, what else could I have told you about g of x that maybe would have made a difference? It's continuous or not continuous, right? So if I would have said, hey, g of x is continuous, then what would be your answer? -5, right? Because then the behavior on either side as well as the value of the function have to be the same. But if I told you that it was not continuous, that would mean something else entirely. So the answer to this is we don't know. Jake was right. We don't know enough information here. I'm going to say we don't know about continuity. If we knew something about continuity, then we could either answer it or we could have a more specific approach and say, well, it's definitely not this or not that, something like that. So, yeah, I could tell you guys were like real cautious about this one, and I'm glad you were, that you really thought it through. I thought you did a really nice job. When you guys come back to school on Monday, we'll talk about the IVT, and that'll close up 1.4. Correct me if I'm wrong, there is no intro video for Monday, right? I don't think there's anything. Let's just look. We can tell if we look in the notes. It's right. Yep, no intro video. All right, have a great weekend. See you guys.